So now here we're looking into example 2 on page 5 of slides 5-2. So this is the function of x and y as well, equals to minus 7x squared plus 88x minus 6xy plus 42y minus 2y squared plus 4. Okay, so here we are to find the point, which is xy, that optimizes this function and show if it is a relative maximum or minimum. So again, let's start with the first step, which is second order conditions. We need to check this. So what we do here is, first we need to derive the first order conditions in order to obtain the second order. All right, so we derive the first order derivatives, okay, so as to get the second order derivative, then to check the second order conditions. So the first one, the original function partialed on x, that is minus 7 by 2x, the first term, plus 88, that's the second term, minus 6y, because here it is 6yx, right? And 6y is a constant multiplier to x. So its derivative is minus 6y. Okay, and then 42y, that's a constant to x. 2y squared minus 2y squared, that's a constant to x, plus 4, that's a constant to x. So the last three terms are disregarded because their derivatives are just 0 with respect to x. Then f partial on y, the first two terms has nothing to do with y, then disregarded. Then starting from this term, it is minus 6x, that's the constant multiplier to y, and its derivative is minus 6x plus 42 minus 2 times of 2y. 2 multiplied by derivative of y squared, which is 2y. Okay, so now we can simplify them. It is minus 14x minus y plus 88. Okay, and we have minus 6x plus minus 4y plus 42. Minus 6x minus 4y plus 42. Okay, so those are the first orders. Then we need to figure out the second order derivatives. Okay, fxx. So now we are working on fx, and then we take another derivative with respect to x. So f partial on x, that's this. Another derivative with respect to x, that's minus 14. The first term. Okay, fyy, that is the derivative of fy with respect to y, and minus 6 plus 42 has nothing to do with y, so the result is minus 4. And then fxy, fx here, then y. Then we need to take the derivative with respect to f partial on x of with f partial on x with respect to y. So the result is minus 6. Okay, so the first one smaller than 0, second one smaller than 0. So we are actually on the track of a maximum here. Okay, and we still need to check the cross term. Okay, so here it is fxx by fyy, that equals to minus 14 by minus 4. Those minuses cancel, so we have 56. Okay, and fxy squared equals to minus 6 squared, which is 36. And here we have fxx by fyy is greater than fxy squared. So the condition also checks. So we have, again, we have a maximum from this. So this is another maximum question. But the difference of this from the previous question, example 1, is that here, as you can see, the first order conditions was pure. The first one is only on x. The second one is only relevant to y. So the solution is kind of easy, but here the solution is more complicated because we, even in the first order derivative with respect to x and first order derivative with respect to y, we still have two variables inside. And then as you're deriving the second order derivative, the fxy is not necessarily 0 as what we had in the first one. Then we do need to take the bother to check fxx by fyy, whether it is greater than fxy squared or not. Okay, because there is a potentiality, that's what we're going to see in example 3, that this just fails, then we don't have a result. We don't have a need to proceed to solving the first order conditions. But here we do check those conditions, right? As you're comparing to this result, we do check. So we do have a maximum. Then it is, and there is no other context for us to check, right? Then here it means that it's worth doing. It's worth to take the steps to solve for the first order conditions. Okay, and there is also possibility, say if you check the first order conditions and you have a maximum, and this function is a cost, and you have no intention to maximize your cost, right? Then here you need to think about the context, how to minimize the cost. Possibly just x equal to 0 and y equal to 0. In that case, the function value is minimized, right? So you work this out, and you need to check the maximum and minimum with the requirement of the context. But here it is a general function. We don't have a context, but you know we're doing a certain optimization, we're doing a maximization. Then it tells you the first order condition, which is the second step, is worth doing. Okay, is worth doing. So let's do that. So here, the first order conditions are just those first two equal to 0. Minus 14x minus 6y plus 88 equal to 0. Minus 6x minus 4y plus 42 equal to 0. Okay, so these are not simplified. We can simplify this by dividing 2 to both sides of each equation. Okay, so we have minus 7x minus 3y plus 44 equal to 0. And the second one is minus 3x minus 2y plus 21 equal to 0. Okay, then here you can see it is a system of equations. If you are familiar with Excel, then you can use Excel to solve for this, right? So what I'm gonna do is here I'm gonna demonstrate to you how to solve this by hand, and later on, in 5.5-4, I'm gonna demonstrate to you, remind you again how to solve this with Excel. So here, what we need to do is to figure out, to find a way to eliminate x and y. Okay, so what I'm gonna do is I'm gonna use equation 1 minus equation 2 which means the left-hand side minus the left-hand side of equation 2, the right-hand side minus right-hand side of equation 2. So the result is minus 7x minus negative 3x, that's plus 3x, minus 3y, minus, again, minus negative 2y, which is plus 2y, plus 44 minus 21, equal to, the right-hand side is 0 minus 0, which is 0. So the first one is minus 4x, the second one is minus y, plus 23 equal to 0. So here, I'll call it equation 3. So what is that? That actually tells you, let's hold on to that. It actually tells you y equals to minus 4x plus 23. I just move y to the other side of the equation. We have this. Then we can take that into any of these equations to eliminate y, right? So let's label 3, and we take 3 into 2 to replace y by x. Then what we have is minus 3x minus 2 times of y, which is minus 4x plus 23 plus 21 equal to 0. Then we need to simplify the left-hand side, which is minus 3x minus 2 by minus 4 is plus 8x, and then minus 2 by 23 is minus 46 plus 21 equal to 0. That is 5x minus 25 equal to 0, which is 5x equals to 25. Therefore, x star equals to 5. When x equal to 5, you take this. So this is labeled as equation 4. Take equation 4 into equation 3. So we have y equals to minus 4 by 5 plus 23, which is minus 20 plus 23, that is 3. Okay, so here we have x star and y star, which are 5, 3, to maximize the function in question. So this is how to solve this by hand. So basically what I'm doing here in the later half is to solve this system equations. And this system equations comes from the first order conditions. And here, as I introduced to you in concepts part, right? How many how many independent variables that we have determines how many first order conditions we will have, because those first order conditions are the first order partial derivative set equal to 0 for each of the independent variables. So we have 2 independent variables, we have 2 first order conditions, and we have 2 equations to solve for 2 unknowns, which are the 2 independent variables, right? That we have to find to maximize or minimize the function in question, depending on what you found with your second order conditions.